This is Vodcast 8A. In this Vodcast, we're going to study, or review actually, stoichiometry and what stoichiometry is. In 8B, we're going to talk about limiting reactants. And in 8C, we're going to get back into percent yield, actual and theoretical yield. So first of all, what is stoichiometry? Here's an example of a balanced chemical equation. In order to talk about stoichiometry, we first have to have a balanced chemical equation. So this unit is going to be based off of last unit. Lots of practice from Unit 7. We're going to go into Unit 8. We started this at the very end of Unit 7 when we calculated the relationships between the mass of the products and the reactants. So stoichiometry is that mole ratio that allows us to calculate how many grams we start with and how many grams we end with. Because there's a law that says the total moles of the elements in the reactants have to equal the total in the product. Same thing is true for mass. The total mass of my reactants have to equal the mass of the products. Well, how does this work? In our balanced equation, on the left side, on my reactant side, how many hydrogens do I have? 4. How many oxygens do I have? 2. On the product side, how many hydrogens do I have? 4. And how many oxygens do I have? 2. Those numbers have to be the same. That's how we balanced our chemical equations. Same thing is true for the mass. If I have 4 hydrogens, my total reactants is 4 grams here. 4.04 with significant figures. If I have 2 oxygens, my total mass is 16 times 2, or 32 grams. 4 plus 32, 4.04 plus 32, gives me 36.04 grams total on the reactant side. If I check my grams on my product side, I know water is 18.02 grams per mole, according to the mass in the periodic table. I have 2 of them. That just proves that my mass on the left, on the reactant side, has to be the same as the mass on the product side on the right. Why are we learning this? We're going to cover several different topics. We're going to get back into energy, with calculating kilojoules for how much energy is required or how much energy is produced. Some chemicals produce energy more efficiently than others, depending on the reaction. So stoichiometry is going to show us the most efficient ratio of reactants in order to get how much energy that we need to be produced, in order to maximize the energy that is produced for that specific equation. We're also going to talk about how your body uses food. Again, we're talking about efficiency. So some foods are more efficient in providing energy or nutrition than others. So nutritionists use stoichiometry when preparing foods and food plans. They use this to calculate how many calories are in. If you look at the nutrition facts on all the boxes or any kind of food that you eat, that's how they calculate how many calories and stuff are in each serving. And then some industrial uses as well. Industry uses stoichiometry to calculate how much raw materials, how much reactant they need to start if they're going to make a product. They don't necessarily want to buy more reactants than they need. If I only need to make 10 things, why would I waste money? That would cut into my profits. I'm only going to buy as much reactant or raw material as I need to make whatever profit I'm trying to make in my product. Here's some examples. This is an airbag in a car. As you can see from this diagram, here's my sensor. When you're in a crash about 15 miles an hour, this sensor will send a signal to what's called the inflator. Inside here, there are 2 reactants, sodium azide and potassium nitrate. That signal that's sent from the crash sensor into the inflator says mix these chemicals quickly. This reaction is highly exothermic, and it produces nitrogen gas. When nitrogen gas is produced, the airbag inflates. The thin fabric that's located inside your steering wheel or inside the dashboard on the passenger side inflates like a big balloon full of nitrogen gas. Now, how are we using stoichiometry to calculate what I need? What if there's too much of those chemicals when the signal is sent to the inflator? What might happen to the bag? Perhaps it gets too big. Perhaps it breaks. We don't want the bag to explode. We want the bag to inflate just at a proper amount so that if you happen to hit your head on it, it's a nice cushion as opposed to the solid steering wheel. What if there's too little chemicals? How much will the bag inflate then? Maybe not as much. Again, you want the bag to inflate to a proper size so that your head hits a nice bag full of air instead of something solid like the dashboard or the steering wheel. How's stoichiometry used in medicine? You see on the ingredients there's different age groups of if you're 6, you're supposed to take this much. If you're an adult, you're supposed to take this much. How do they use that? Well, talking about Tums, here are some active ingredients. When do you take Tums? When your stomach hurts. Why? You have too much acid. Thinking back about our reaction types, if you have too much acid, you want to neutralize it by adding some kind of base. How do we know something is a base? Hydroxide. So the active ingredients here are magnesium hydroxide, sodium hydrogen carbonate, calcium carbonate, and aluminum hydroxide. The products that contain the carbonates or bicarbonates produce the carbon dioxide and water. Therefore, you burp a lot because that gas, the carbon dioxide gas, needs to come out somewhere. And the products that have the hydroxide, this would be my aluminum hydroxide and my magnesium hydroxide, are actually what neutralize, remember, neutralization, double displacement reaction, neutralize the acid in your stomach and hopefully make you feel better. If you take too many, or if the dosage is off, what may happen? If you neutralize too much acid, you can't digest properly. What if you don't take enough and you don't quite feel better? So they use stoichiometry to calculate the proper ratio, the proper tablet size that you should be taking for these common problems. Baking, cooking. Anytime you bake or cook, it has to be a stoichiometric reaction because each recipe tells you how many, if we're making brownies, how much oil and how much water and how many eggs to add. So every time you bake, you're actually using a chemical reaction. Stoichiometrically, it has to be balanced because what if you add too much or too little of one ingredient? What if I add too much water to my brownies? Add too much oil? Not enough eggs? Probably not going to taste right. So, if you don't follow all of the requirements in the balanced reaction, if I need 1 box, let's cheat, of brownies, and a half a cup of oil, and a half a cup of water, and 2 eggs to make some yummy brownies, what else do the directions, do the reaction tell me? It tells me, over the arrow, my conditions for which this reaction must occur. It may say 350 degrees for 25 minutes. If you don't follow all of these conditions, it's not going to taste right. If you don't heat it in the oven for 25 minutes, you're not going to get very yummy brownies. So, how are we going to use it? We're going to go back to our moles and grams and molecules conversions so that we can determine or calculate how much product we can produce with the amount that's given in each reaction of the reactants. How do we do that again? We use our friend the snowman calculation. You see we've added one more here. We're going from moles to molecules the same way as we did before using Avogadro's number. We're converting between grams and moles the same way as we did before using the molar mass from the periodic table. Now we've added density. Density will always be given to you. You just have to know how to calculate it, and density is going from grams to liters. How would this look in our snowman? Well, now our snowman has a hat. If you're going grams to liters, you divide by density. If you're going volume, liters, or sometimes milliliters to grams, you multiply by the density. Again, when you draw this out on your FLM thing, whatever units you have up top here, they have to cancel with the ones on the bottom. So if you're not one of those people who memorizes, okay, if I go this way, I multiply, if I go this way, I divide, just watch your units and they'll cancel out just like always. So let's try some of this. This should be a review from the last unit. So if you want to pause the video now, you can read these. This is our review of how to calculate, how to write a balanced equation. You can pause this right now and finish the two problems that are given and then just check your answers at the end. Or you can follow along with me the whole way through. What do we have to do first? Obviously read the problem. Write the balanced equation. Figure out what molar masses we need. If it helps you to put them in a table, you can make a table. Write down what's given from the problem in your table. Figure out how we're going to convert, and then use the factor label method to solve for what it's asking for. So here's our first problem. Chromium reacts with oxygen to form chromium 3 with a 3+ charge oxide. First step, write the balanced equation. Chromium, Cr, reacts with oxygen, don't forget, it's diatomic, to form chromium 3 oxide. Since chromium is a 3+ and oxygen is a 2-, Cr2O3. Now I have to balance 3 oxygens and 2. Will be a 3 there and a 2 here. That gives me 4 chromium, so my ratio is 4 to 3 to 2. Now, if you want to fill in this table, you can fill it in with the molar masses. The molar mass of chromium is 52.00. The molar mass of oxygen is 32.00. Again, my units are grams per mole here for my molar mass. And chromium oxide is 152 grams per mole. So, how much do I have? What am I given? I'm going to solve part A. How many moles of chromium? So I'm solving for moles of chromium. That's my unknown. I don't know how many moles I have. How many moles of chromium are needed to produce 100 moles of chromic oxide? Where do I start? Always start with what you're given. 100 moles of chromic oxide. Now, if you're thinking snowman, I'm in moles of chromic oxide, which would be here, and I want to get to moles of chromium. One step, I just need my mole ratio. I put the 2 moles on the bottom because I get that from here, my ratio, and my ratio is 2 to 4. 100 times 4 is 400, divided by 2, I would need 200 moles of chromium. My units cancel, and we just multiply. How about part B? Change color here. Part B. Now, how many grams of chromium? Now I'm looking for grams of chromium. I'm trying to get to grams of chromium, so I'm looking on my snowman, are needed to produce 1,000 grams of chromic oxide. Now what do I have to do? How many steps is this going to be? First I have to take grams to moles, then do my mole ratio, and then go moles to grams. This one's going to be 3 steps. Where do I start? I have 1,000 grams, my last one, and I want to go grams to grams. Still always start with what you're given. 1,000 grams of chromic oxide. First step is convert grams to moles. What number do I need down here? The 152, because my grams have to cancel, and there's 152 grams in 1 mole of chromic oxide. Now I'm in moles. I'm over here. Converting moles to moles, I need a mole ratio. My same ratio from before. How do I know what goes on top? I have Cr2O3 on top, so I need again the 2 to 4 ratio, because Cr2O3, chromic oxide, has to cancel top and bottom. And now I'm in moles of chromium. That's my second step. I wanted to get to grams. Now I have to convert moles to grams again using the mass of chromium. I have moles up top, so I need moles on bottom. 1 mole of chromium is 52 grams. Everything cancels. If you multiply 1,000 times 4 times 52, divide by 152, divide by 2, you should get 684.21 grams of chromium. Same reaction. You can copy your balanced equation here for chromium plus 2 oxygen, not 2, 3 oxygen, goes to 2 Cr2O3. Now I'm in moles, and I want to get to liters. Again, I have to give you the density. Here's the new part. Have to give you the density. But you start exactly the way we started before. Always start with what you're given. 65 moles of chromium. I'm right here in moles. And I want to get to liters of oxygen. So somewhere, because I'm swapping from chromium to oxygen, you know you're going to have to use this ratio now. Moles of chromium up top, the 4 has to go on the bottom, and the 3 moles of oxygen on top. Moles cancel, moles of oxygen now. I have to get to grams, again, look at your snowman, you have to get to grams before you go up to liters. So 1 mole of oxygen, on the previous slide, we said was 32 grams of oxygen. And now here's my new conversion factor, 1.43 grams. Why did I put that on the bottom? So it would cancel out. 1.43 grams equals 1 liter of oxygen. Punching those numbers in on your calculator, you should get 1,090 with sig figs liters of oxygen. Part D. 6.50 moles of chromium. I'm still in moles of chromium. Now I want to get to molecules of chromic oxide. How many molecules? Well, this tells you 2 things at least. The ratio that at some point you're going to use to jump substances is 4:2. And since it says molecules, we'll need to go back and get our best friend Avogadro. So, starting where we always start, with what we're given, 6.50 moles of chromium, moles up top. Here comes my ratio. 4 moles of chromium is 2 moles of Cr2O3. Now I'm in moles. I wanted to get to molecules. Thinking of snowman, you're in moles. I did my mole ratio. Now I want to get to molecules. So I multiply 1 mole of Cr2O3 multiplied by 6.022 times 10 to the 23rd gives me molecules. Specifically, 1.96 times 10 to the 24 molecules of Cr2O3. We have one more example. Again, here's your balance. Nope, this isn't balanced. You have to balance it. Here's your equation. Pause the video now, try and balance it, or follow along if you need to. Since I have 2 sodiums over here, I'm going to need 2 on this side. That gives me 6, 10 oxygen. Here I have 4, 6, 2 carbons for this side, 8, 10 oxygens now. That gives me 4 hydrogens on the right. 2 plus 2, that should be balanced with a 2:1 to 1:2:1 ratio. If you want to pause it here, try a couple of these examples. They're just like the last ones. Or if you want to follow along, we're going to start with A. Starting with 5 grams of sulfuric acid. Grams? What mass of NaHCO3? Now I'm doing a gram to gram calculation. Grams to grams. Snowman, I have to go to moles, that's 1. Mole ratio, that's 2. Back up to grams. It's going to be 3 steps. Look at your snowman chart if you need to. Starting with 5 grams of H2SO4. Grams up top. What has to go on the bottom? I have to cancel out grams. H2SO4, the mass is, if you calculate it, 98.09 grams in 1 mole of H2SO4. My ratio this time is 1:2. 1 mole H2SO4 gives me 2 moles of NaHCO3. But I don't want to be in moles, I want to be in grams. So I need step 3. 1 mole of NaHCO3, I have to go back to grams. 84.01 if you add them all up. Moles cancel moles. I'm in grams. If you punch that in your calculator, you should get 8.56 grams of NaHCO3. Part B. Grams of water, still starting with the 5 grams of sulfuric acid. Still starting with grams of here, sulfuric acid, trying to get to water in grams. Grams to grams, still another 3-step calculation. My ratio again is going to be 1 to 2. So I start with what I'm given. 5 grams of H2SO4, same mass, 98.09 grams in 1 mole of H2SO4. Now I need my mole ratio, which is 1 mole of H2SO4 gives me 2 moles of water. But it didn't ask for moles of water, it asked for grams. So 1 mole of H2O is 18.02 grams. Moles cancel with moles. I'm in grams of water. It took me 3 steps. If you calculate that, I get 1.84 grams of water. So those are stoichiometric calculations. You can go grams of, we started both with H2SO4. You can calculate to anything. The only thing that changes, maybe, is going to be your ratio and probably, or most definitely, your molar mass. 2 more parts, C and D, with our balanced equation. Now, it wants me to get to molecules of carbon dioxide. Molecules of carbon dioxide. Still starting with my 5 grams of H2SO4. Ratio again, 1 to 2. Now it says molecules, though. Now we're thinking bottom of the snowman, so I need my Avogadro's number. 5 grams of H2SO4. Same thing. Grams. I have to get out of grams and get to moles. So I need the 98.09 grams. The molar mass of sulfuric acid gets me to moles. My ratio, 1 to 2. Putting the 1 on the bottom, because that's where I'm at. H2SO4 has to cancel to 2 moles of CO2. But I didn't want to be in moles, I wanted to be in molecules. So I multiply by Avogadro. 6.022 times 10 to the 23rd molecules is 1 mole of CO2 to cancel that. And if you calculate that, you should get 6.14 times 10 to the 22 molecules of CO2. The newest part to our calculation. Now I'm going to add density. Density is always given. Here's grams per liters. It says how many liters of carbon dioxide gas. Now I don't want molecules. I want liters of CO2, still from my 5 grams. So I'm still going to have my 1 to 2 ratio, but now I'm going to use this conversion somewhere. Go look at your snowman. We're going to start at the top of his head on the first snowman, and we have to go over to his hat on the next one. Again, that's going to be how many steps? Grams to moles, 1. Mole ratio, 2. Moles to grams, 3. Grams to liters, this guy's going to have 4 steps. Always start with what you're given. 5 grams of H2SO4. I need my molar mass again. 98.09 grams of H2SO4 is 1 mole of H2SO4. I got to get my ratio 1 to 2. The 1 has to go on the bottom because that's set with the H2SO4, 2 moles of CO2. But I don't want moles, I want liters. In order to get to liters, I have to first get to grams. So 1 mole of CO2, to cancel out with this mole, looking on the periodic table, is 44.01 grams of CO2. Not quite there yet, that's my third step. Now I have to use the density, which is specific to each substance, so that's why I have to give it to you for each problem. 1.977 grams is equal to 1 liter of CO2. Punching that into your calculator, I got 2.27 liters of CO2. Those are our 2 examples. Everything cancels out. We can convert to molecules, we can convert to liters, we can convert to grams, to moles. This should be a review other than the density problems that we've added to the liters from Unit 7. So if you have questions on this, you want more practice, make sure you please come in and see me. We'll make sure you get this down because the next part B, video B, we're going to add a slight little twist to it.